This video has been supported by PCBWay. Hey guys, here's what I hope to be a cute little accessory for our upcoming excursion into resistance metrology. 200 dozen. Oh no, it's actually a spaceship control console. Wait, no, wrong again. It's a Guildline model 9930. Direct current comparator potentiometer. What an unusual arrangement of words. This has to be the chunkiest potentiometer I've ever seen. Damn. What they mean is a potential meter, a voltmeter nowadays. But it's the other part, the DC comparator, that made my eBay trigger finger twitch. If what I hope it is actually in there, I paid a good price. If not, I overpaid massively for 70 kilograms of scrap. This is the goal. I mean, unsurprisingly, 10.5 digits. 0.1 parts per billion resolution, and 15 ppb accuracy in some settings. It compares resistances to one another in an unusual, clever way. Really the only way to get that kind of performance. And I hope my spaceship console is based on the same thing. Think of it as sending 1 ampere through 1 transformer winding, and minus 100 milliampere through 10 transformer windings. The resulting magnetic fluxes would cancel each other out, and the resulting net zero flux density in the transformer core happens to be conveniently precisely detectable. More about that in a minute. The advantage of that over, say, a comparison through shunt resistors is that numbers of transformer windings don't have temperature coefficients or long-term drifts. They are forever exactly 1 to 10 or whatever. A significant disadvantage of this, and the reason why I unsportsmanlike grabbed this eBay relic, rather than simply making such a comparator myself, is a long list of arcane materials and processes needed to pull this off. I'd have to raid molten core hundreds of times for the enchanted, nickel-iron supermalloy, grain-oriented, extreme permeability sheet metal, and then after shaping that into toroids it needs a special hydrogen annealing recipe, and multi-layer magnetic shielding with similarly unobtainium metals. Even for the largest scientific project in the world, it's not easy to source this stuff. So sportsmanship or not, I'll be very happy if I find such a device in here. But before harvesting anything, I would like to dedicate the video to this Canadian marvel from the 60s. It is mind-blowing in its own right, and it would be a tragedy if the last survivors of this series vanished without ever having left an imprint on the internets. The first things I noticed are a low thermal EMF pure copper patch field full of unknown abbreviations. A quantity of spider poop that validates the assumed age of this thing. Unlabeled rotary switches for a surprise primary current. Atomic age electrolytic capacitors, which I will not be preventively replacing, by the way. Not for this one test run. A light bulb-based Nanovolt amplifier, and a lot more goodies. I hope I'm not the only one who has never ever heard of that before. Let's try to understand, repair, and maybe even use it. That shouldn't be too difficult. This is primitive 1960s technology, right? We'll see about primitive, but the age of some parts worries me admittedly. So for a first careful power on, I'm going to spoon-feed it power with a programmable AC source. As soon as it sees excessive power draw, it will flip the switch. Then we can re-evaluate strategies without burning out any transformers. But power intake looks okay. No magic smoke, no fireworks forthcoming yet. And nothing else either. A few initial problems were easy to spot, like some solid core wire had broken off. And I don't think I was the only one to ever get caught by surprise, by the weight and depth of the front panel. There's this bottom row of precision resistors on rotary switches, just perfectly positioned to get squished when prematurely setting down this whole assembly on this wooden ledge. I choose to believe that that must have happened a couple of times to this thing, and it wasn't just me. This whole tray module just slid out of the side of the instrument. It's completely alien technology to me, but there is a light bulb missing, that much I can tell. This seems to be an electromagneto-optical and electrochemical device. Usually I have a good intuition for all things technical, but here I'm drawing a complete blank. I hope we can get some signs of life and that the bigger picture will put this into context. I've measured the incoming light bulb voltage here and I'm adjusting the series resistor for an LED replacement. Its output then gets collimated, shaped, and projected by a mirror galvanometer onto 3 phototransistors, it seems. Meanwhile, the relay seems to be quite busy laying the re. But this looks functional now. Maybe a new light source was all that this thing needed. We will return here later to make an attempt at comprehension. Hey, if you're here, that means you're a fellow precision fanatic and you're going to love this one. Together with PCBWay, I made the most affordable high-precision digital thermometer ever. It's just a TMP119 sensor IC, to be honest. But with PCBWay's amazing flexible circuit board material, this can do almost everything. I've given it a hole to hang or screw it places. It can just be an ambient air probe as is, and send readings over Wi-Fi into a database. Or we can use the built-in battery management and turn this into a long-term data logger to accompany sensitive shipments. Another thermometer with this kind of flexibility doesn't exist. And one with this kind of accuracy can cost you hundreds or thousands. If you use PCBWay's convenient turnkey assembly service, they'll build you one for a lot less. Or if you just order the raw PCBs and do it yourself, like I did, it'll be even cheaper. Either way, PCBWay, always fast, reliable and affordable. Give them a try with a link below. Back to Guildline. That simple light source replacement appears to have given us a 50 mA primary current, if that IP panel meter on the right is to be believed. It's plausible, because look, if we send that primary current somewhere, the effect on the comparator balance, the central meter, is quite clear. However, I thought that normally the secondary current is automatically adjusted in polarity and magnitude to compensate for any imbalances. That is very important, because a large imbalance can permanently magnetize the comparator core and degrade its performance in the long term. What? Why didn't you say so earlier? Finding out why that wasn't working without any schematic diagrams was very difficult.
Why is it here? What?
Allow me to elaborate what I mean by that. This is the slave current supply, it says so on the rear, that should deliver that secondary current. There are 3 wires coming out of its output. One goes to this unknown rotary switch. In positions other than read, it sends it right back to the cart, through a low-value resistor and to ground. The second wire goes to this secondary current panel meter, and then to an intermediate front panel connector, where it vanishes in another wiring harness. From that it re-emerges at this reversing switch, and then it goes all the way back home, to the low thermal EMF patch panel, bridge number 1. I swear if I have to say front panel one more time. And then of course it has to go back to the front panel, just as a yellow wire this time. Not like to do anything there, just passing through to this precision resistor assembly. And when after that it still didn't seem to be heading towards the actual comparator toroid, which should be this guy up here, that was where I lost patience. And then I just swapped the old Soviet op-amp on the slave current supply card, which, as it turns out, was the problem all along. How lucky. With that it looks like we are mostly in business. And it's going to get even better, check this out. I did not expect that this would lead anywhere, but I thought I'd write Guildline HQ, still in Canada, and ask for some documentation. Not only did they reply to some nobody not customer on the other side of the planet, they actually still had some 1960s manuals for this thing. And they just sent over a copy, completely unproblematically. A huge thanks to the legends at Guildline Instruments. No schematics, but these detailed manuals will take the guesswork out of our exploration. The DCV linearity, also depending on transformer turn ratios alone, happens to be better than my finest 3458As, whose ADCs have to work with charge injection, dielectric absorption, power coefficients, variable switch resistances, comparator offsets and all that kind of funny business. I was going to give this the Unsafe Warnings Cursed Technology Award at first, because of the light bulb stuff, which is a bit eccentric to be fair. But a comparison of 2 transformer currents is actually blessedly pragmatic. And because it's all current-based upstream, it doesn't even care about thermal EMFs or resistances in all the control switches. These could just be replaced with cheap, low-quality relays for automation. But that's skipping many steps. Let's see if it works as intended. Main power switch, heater power switch for a built-in voltage reference. That should have been on for 24 hours in advance, but we don't need ultimate stability right now. Constant primary current source. This can be considered 50 mA. The fine adjustments in the bottom row are only for some special scenarios. This primary current goes through measure number of windings, none, so the comparator is balanced with no secondary current. The number of secondary windings is 1000 plus standardize, so just 1000 at this setting. The standardized dials can be used for fine-tuning or standardizing the whole potentiometer, if its built-in reference or other parts have small offsets. Let's send our 50 mA primary current through 2000 windings. That would be 100,000 mA turns. To maintain comparator balance, the slave current supply has to send 100 mA through its fixed 1000 secondary windings. 100,000 mA turns again. And it does. Excellent. The secondary current also goes through a resistor, which the manuals call the forcing resistor. That generates a voltage. And finally, the purpose of the Nanovolt amplifier and this upper light beam galvanometer is to find out exactly when that voltage and whatever we wanted to measure are equal. Yeah, putting it like that, it may sound a bit crazy in comparison to just taking a DMM measurement. But again, a DMM measurement depends on countless non-ideal components and their interactions. Whereas this can be standardized to a voltage standard. And then we can make arbitrary voltage measurements approaching perfect linearity, depending only on a constant current source, one resistor, and eternally stable comparator winding ratios. There does seem to be one more little problem. Since this system's main purpose used to be Western cell comparisons, vulnerable single-use precision batteries, I would be very surprised if it was meant to periodically help itself to over 10 mA input bias current. No Western cell would leave this measurement unchanged. Yet the SMU's milliampere indicator blinking shows that that compliance setting is reached occasionally. That might just be my lenient capacitor preservation policy coming to stab me in the back. These large filter cans should not have over 100 mV of RMS ripple on them. And I don't think they should have cancerous growths on them either. Such early analog circuits typically don't have very good power supply ripple rejection. So something like this could leak into the secondary current and cause strange effects there. Here's an amusing side-by-side comparison with modern electrolytics. Similar characteristics, but I'm not sure if these will last for 60 years too. Yes, with those swapped we are getting a reasonably stable voltage on the EMF terminals. And if we now apply exactly the same voltage to those terminals, that should satisfy the Nanovolt preamp and cause a zero reading on the upper light beam galvanometer. Dexter is not completely convinced by this explanation, but I've connected 3458A in parallel for fact-checking. We should also be able to see the absolute lowest input current on the SMU exactly at this balance point. The 1, 2, 3, 4 and R push buttons on the left side are sensitivity settings before the Nanovolt preamp. So if we don't know the voltage that we are measuring, we can search a wide range without blowing anything up. The push buttons on the right side are functions and ranges. Times 1, times 0.1, and times 0.01 select which forcing resistors are placed into the path of the secondary current. Therefore, they are the voltage measurement ranges. 2 volt, 200 mV and 20 mV, and that's all the voltage ranges there are. The upper left-hand rotary switch is a sensitivity setting after the Nanovolt preamp. So just a divider for light beam galvanometer sensitivity. It looks like we are slowly homing in on 996 mV. Oh no, 997 would have been too much. How about 996 mV and 230 microvolt? That looks pretty good, but what does 3458A think? Yep, 99623. versus 99629. I can live with that. That's a 60 microvolt or 60 ppm disagreement, but one participant has just been resurrected and not given enough time to acclimate. That should just be a fixed DC offset. If everything else is right, its linearity should be unaffected. Guildline specifications say 0.05 ppm of range or better, in all three ranges. They didn't have Josephson voltage generators to verify that, but I tend to believe it. There's just no possible source of nonlinearity. Meanwhile, 3458A, today's world-famous linearity reference, guarantees only 0.1 ppm of its 10-volt range. Its 1-volt range is looser at 0.3 ppm of reading plus 0.1 ppm of range. Impossible to say which one is the most trustworthy, but I thought I'd make a few quick linearity comparisons to see if everybody is at least close to their datasheet specs. I've never tested the 1-volt ranges of my 3458s before, and while I do agree that there is no large systemic source of nonlinearity in the Guildline potentiometer, it does generate voltages by sending 0 to 50 mA through resistors, so there could very well be a visible power coefficient. Also, it's crazy vibration sensitive. Hello, anybody home? Do you have a minute to talk about our Lord and Savior, the ppm? So in this unmodified original state, we might not be seeing the absolute peak performance that the direct current comparator system is capable of, but when I'm done with it, oh boy, just you wait. It's very promising already. Hell, it's incredible for a 1960s product. Let's rip it apart and uncover some forgotten techniques of the 1960s. I do have to be a little bit careful because the actual comparator toroid, the thing I'm keeping, has like 1 million pins and I know none of them. It would be somewhere between extremely tedious and impossible to figure those out with only the toroid in front of me. I'd much rather map out the connections based on the switches and the control cards. Wow, that was a heavy copper sheet metal cover. They don't make them like that anymore. OMG, if I had known about this, that would have made the initial repairs so much easier. I've been doing keyhole surgery through the small sideways openings. I couldn't believe this guy at first, but it actually does what it says. There's just one big catch that limits its usefulness today. Here we go, the one relatively small component that I'm doing all of this for. The many-pinned magnetic donut. The one and only direct current comparator toroid. Actually, there might be at least 11 others, unless they ended up getting melted down for copper recycling. You know, this guy works out. It's as thick as they come, but the manual and logic says that in order to give us 7-digit measurements, with those 7 measure rotary switches, it needs to have over 2 million windings. That seems a bit unrealistic. Some quick conservative estimate, assuming the smallest gauge copper wire, which we are evidently not using here, always comes out to hundreds of kilograms of copper. So there must be a trick somewhere to make this physically possible. I'm very curious, but I'm not going to take this one apart. Instead, for our edutainment pleasure, here's a more modern, lower quality, zero flux detecting DC comparator core, stolen from a Danfossick Ultrastep 866. Same principle but fixed ratio windings, except not anymore. In order for these guys to detect the exact point where zero flux density occurs, where the primary and secondary ampere times turns are exactly equal, the internal detector depends on the highest magnetic sensitivity possible, and for that to not be disturbed by the surroundings or the earth, they need extremely effective magnetic shielding, which this bright and shiny bare metal shell is a part of. You can't let that go all the way around the core, or else it would act like a shorted winding in a transformer. That white interior wall section has to serve as magnetic shielding as well, while not being electrically conductive. Magnetic field lines cannot be stopped or interrupted, only redirected by suitable materials, so the geometries involved are not always intuitive. To not damage or deform this special alloy shield with a prying screwdriver, I printed this fixture for gently loosening the glue and lifting the two halves off of each other. Ta-da! Oh, interesting. We've got a labyrinth seal machined into the solid metal shell, followed by a few layers of what looks like amorphous sheet metal. Super fragile, glass-like, brittle, but with unique magnetic characteristics. If you buy nanocrystalline or ultra-permeability magnetic components, those are made from this stuff. The inwards-facing gap in the outer shell is sealed by what looks like an off-the-shelf toroid, and the two remaining rings are the actual detector and modulator cores. They have a small cross-section, they are also made from a high permeability material, and they have wire windings of their own. They are connected in series opposition, and an alternating current is sent through both, deliberately driving them into saturation. So in one half cycle, current goes in here, and on the upper core goes in this direction. That direction is reversed on the other core, and so is the resulting alignment of the magnetic dipoles. Once all are aligned, the cores don't oppose the current flow anymore, and the voltage over them sinks to nothing. The excitation current is also alternating. I think they aim for a 700 Hz square wave. Under the influence of no foreign external magnetic fluxes, these cores will saturate in perfect symmetry. So if we were to look at a voltage waveform on the center tap, that too should be perfectly symmetrical, equal length positive and negative half waves, if there is anything at all. However, if there is any external flux present, say when the outer ratio windings are not in ampere-turn balance, that would support the saturation of one core and counteract the saturation of the other core. Suddenly the center tap signal would no longer be symmetrical. A demodulator circuit can help detect and turn such an imbalance into a DC voltage, which can then serve as feedback in a comparator balance control loop over secondary current. That is the central idea of all this. I'm sure the affordable Danphysik Ultrastep does exactly the same thing as the invaluable Guildline relic. The latter might just have a bit more of everything. Here's what I've found out about it so far. It does not have over 2 million windings. Instead, on the least significant windings, which are only worth 100,000th of full scale or less, so with any errors getting attenuated by that factor, they simply use resistive dividers to feed the dials, and then they are connected in parallel to just one physical actual decade of windings. It's virtual partial windings that behave exactly like the real thing. In columns 8 and 9 we've got some interesting isolated transferable windings, which can be made a part of either primary or secondary for a kind of baked-in linearity self-test. And down here we've got the actual innermost modulator and detector windings coming out. This upper floor has a pretty normal multi-voltage power supply, an auto-transformer for internationality. This long module, which they call transformer box, seems to be mostly support for the square wave oscillator modulator, this transformer being directly connected to the innermost DCC cores. The central black box contains the highest sensitivity light beam galvanometer, with which the Nanovolt amplifier is read and the exact point of EMF balance is determined. There's a brand new LED replacement, a focal lens, and the actual galvo, a mirror suspended in a fluid-filled vat, pointing at another articulating mirror, which in turn projects the light beam onto this front-facing divided screen. And here is once again what I now understand to be the opto-magneto-electrochemical constant current source. Guildline points out multiple times that their product does not depend on multiple critical resistors. So how on earth did they build a constant current source, suitably superbly stable, for top-level metrology? Well, it starts with a black box, that's a foam-insulated outer shell. In there lives a thick copper cup, bonded to which is resistive heater wire and a highly sensitive mercury thermometer. This thing is slowly heated unless the mercury closes an electrical contact, at what I would guesstimate to be 26 or 7 Celsius. In there is another copper subcup, acting as a thermal low-pass filter, smoothing out what is, if we are being honest, a bang-bang controller. All this effort to keep a Western cell happy, a little saturated mercury-cadmium battery. And happy it is, miraculously, even though it's nearly 60 years old. These must not be loaded, in no sense of the word. They are not rechargeable and the smallest current flow will change them forever, ultimately depleting them. But this guy's lifetime job was to actuate another extreme sensitivity mirror galvanometer, yet it still seems to be at its nominal voltage of around 1.018. How did they make it work for so long without depleting it? Well, thank you, I've been hoping for that question. They are connecting that precious pampered standard cell and the mirror galvanometer in series, and that string shunts what I would describe as a pretty critical resistor. The 50 mA primary current, this thing's whole purpose, has to flow through this resistor, and that creates a voltage. The critical resistor is chosen in such a way that at 50 mA it develops exactly the Western cell voltage. So we've got 1.018 over the resistor and over the Western cell, balancing these two branches perfectly, so no current will flow into or out of the Western cell and none through the mirror galvanometer. If adverse ambient conditions or an idiot YouTuber knocking on the enclosure ever caused an imbalance here, then a small current would flow through the extremely sensitive galvo, but only for a split second, because its light spot is observed very carefully by the upper two phototransistors. If one gets illuminated more than the other, a light-sensitive amplifier steps in, acting like a variable resistance, counteracting like a variable resistance actually, trying to recenter the beam by steering the current back to 50 mA. The central lower phototransistor should always be illuminated. When the beam is centered, the control loop stabilized, and the zero Western cell current condition can be ensured. When there's a malfunction, however, or a simple burnt-out light bulb, that might not be the case, and the pricey voltage reference might be damaged. So it is the purpose of this extravagant, customized, low-leakage current relay to safely disconnect the Western cell from everything when the central phototransistor is not illuminated. Low leakage current until today. Yeah, that's about it for one of the most constant current sources of all time. I'm not sure what the purpose of this knob is. It rotates the base of the entire galvo slightly. But that shouldn't really change the 50 mA, or am I overlooking something? Please leave a comment if you have a theory. And here it is, the extreme sensitivity galvo. What, is that mirror cracked? It's certainly submerged in a damping fluid which suppresses noise above a few hertz. Delicious pure copper low thermal EMF terminals. I might have to retract my previously expressed doubts about power coefficient of the forcing resistors posing a risk to linearity, because this solid few kilogram brass chunk appears to be home to the all-important forcing resistors. They are just wire wound around the perimeter, providing excellent thermal coupling and a gigantic time constant, plus temperature coefficient of thermal expansion of brass and manganese wire should be very nicely matched. I also love the way they are burying the solder joints between resistive elements and interconnecting wires deep within the brass block to ensure that those two are always at equal temperatures to avoid thermocouple effects. The user interface has another luxurious copper can, under which the range and function push buttons are hidden. It seems like at this point in the circuit thermal EMFs do matter, because there's foam insulation to where an operator might rest his hands. And the solder in here looks different to everywhere else in the system, maybe a specialized alloy? Yet another application for delicious cadmium maybe. Since I've already shown you what these guys could pull off with mirror galvanometers, you might not be quite as shocked and confused as I was upon seeing the light bulb-based Nanovolt amplifier. But yeah, this is crazy. I can't quite figure out what they are doing in here through this small peephole. So thank you for watching and see you next time. Okay, final exhibit of the day. This device doesn't really have its own power cord. Only nanovolt inputs, millivolt outputs, and a hole for the light bulb to shine in. The lamp housing does have a power cord, but you know what I mean. This thing is powered by light and nanovolts. And therein lies the small weakness that I mentioned earlier. In contrast to typical modern meters and amplifiers, this device has a very low input impedance. 3.6 kilo ohm maximum, I think. The ultra-low input has to drive and move the mirror galvanometer, and a pair of photocells has to drive the output. That's not optimal, but in suitable circuits it works. Our potentiometer puts this thing into a very low impedance context, so no problems there. The working principle this time is that there are two photocells behind the white masks. Light can reach them through two slits each. Electrically they are connected in parallel but with opposing polarities. Currently the right one gets much more light than the left one, so their combined output is going to be railed. That's because I haven't installed the feedback resistor yet. That one gives negative feedback, opposing the input and steering the mirror galvanometer back to center. This feedback, or how hard the photocells have to counteract the input, is a highly amplified but nicely proportional representation of the input, so it also serves as the output of this amplifier. In normal operation, while not overloaded, we don't even see the light pattern move at a changing input, because the negative feedback is successful at keeping the exposure of both photocells equal. Overall, another very cute device, built with craftsmanship and creativity the likes of which we might never see again. But for me it's too vibration sensitive, so I'm sticking with my Keysight 34420A. And that is finally all. I think we've poked at everything interesting. Now it's time for me to modernize the support infrastructure for my Comparator donut. Once again, huge thanks to Guildline for the invaluable documents. And huge thanks to you for nerding out with me today.